Hey everyone, this is our Team Teach. It's Module 4, Chapter 11, Transformations, Symmetries, and Toweling. We are to infinity and beyond. I am Jess Sullens.
I'm Regina Lusby.
And I'm Danielle Gillham.
And we are one team member short tonight, so it's just going to be the three of us. So let's get started.
All right, Regina, what is rotational symmetry?
Okay, so rotational symmetry is when you rotate an object, and it can be anywhere up to 180 degrees, and it will look exactly the same when you totally flip it over like that. And that's rotational symmetry.
Very neat. Thank you, Regina.
Mm-hmm.
I like your colors on here as well.
Thank you. All right, Jess, what would happen if we rotated this figure 360 degrees instead of 180 degrees?
Well, if we rotate it 360 degrees, we know that is a full circle, so that's all the way around. The 180 degrees is only a half circle. So if we were to rotate this 360 degrees, it would actually end up looking exactly how it looks on our screen right now. It would be back in the same position as it is already in. So
that
would
makes
be a
sense.
360-degree rotation. I'm trying not to sneeze, guys. Are y'all's allergies bothering y'all lately?
Yes, very much so.
All right, Danielle, what like if it was flipped over the line?
So if we were to flip this over the line, it would just be like what we call a mirror reflection.
Mm-hmm.
And it's going to just look sort of like this. So it's
Okay.
just kind of, if you had a mirror up to this shape,
Mm-hmm.
it's just basically flipped.
Okay, I see that. Just completely over. Awesome.
Hey, Regina, what is reflection symmetry?
Okay, so reflection symmetry, it's kind of like a mirror symmetry, and it's when you have half of something on one side and then the other half is exactly the same. So like if you drew a line right down the middle of it, it would have to be the exact same on both sides. And a figure can have more than one line of reflection in it. So it could only have one, it may not have any, or it could have several.
All right.
Thank you, Regina.
Mm-hmm.
Very detailed. Thank you.
Mm-hmm.
Looks really good.
Mm-hmm.
So Jess, what does it mean for a shape to be symmetrical?
Well, like you were saying, for a shape to be symmetrical, it has to have one line of symmetry. And what that means is we could draw a line through a shape, just like you said, and it would be the same on each side. So
Okay.
we've got two shapes here. This one's a kind of a wonky looking shape over here. And if we look at it, it looks like, oh, maybe we could fold this and our corners match. But we can't. When I think of looking for a line of symmetry, that's the first thing I think of is like folding paper. So if we folded this in half, we would go straight down, and like we're thinking of like hot dog hamburger style folding. This shape would never match up. This line on this side is not equal to what is on this side. So this one is not going to be a symmetrical shape. There's no way that we could draw on it to make it symmetrical where both sides match over our line. So we're going to put a bigger X on this one and mark it out again. If we come over here to our diamond or our rhombus, we're looking at it, and if thinking of this as a piece of paper, we automatically can see that if we went straight across here and put this top flap down here,
Mm-hmm.
then we actually would have a symmetrical shape. So it has to have at least one line of symmetry, but it can't have more than one. And here we do. So we could actually fold our paper for our shape again and do corner to corner, and we would have another line of symmetry. So it has to have at least one, but it can have, as many as it could hold for that shape.
Mm-hmm.
So it's the mirrored line on each side, and that's how we would make a shape symmetrical.
Okay, thanks for explaining that.
Thank you for that.
All right, Danielle, can you explain a little bit what is rotational symmetry?
So rotational symmetry is, let's see if it'll let me draw. Oops. Okay. So basically, this triangle, all the sides are the same. So if you were to break it into 3,
You're very good at drawing with this. My hand is
Yes.
not that steady. I am very amazed right now, Danielle. Great job.
so now that we have 3 parts,
Mm-hmm.
basically if we were to do 120 degrees, this flipped over here is 120 degrees. So that's just rotational symmetry, just rotating it to the degrees that it tells you to.
Okay. Yeah, I could see that. I actually had not looked at it as being that way. So I like how you did this. That was a great explanation.
Thank you. I don't know how to clear my things though.
Is it giving you that little clear option at the top?
Sorry guys. Hold on.
It happens.
Computer technology, it's just amazing how much we're actually able to do and how all these kids are doing schoolwork online right now with Zoom.
Yes.
Very interesting.
They are way more advanced than we definitely were at their age. And
Absolutely.
it's amazing what they can do.
Oh, I've been looking at some of their work stuff, like, oh goodness, I'm a little intimidated, but I will help you do what I can help you do. What do you need? Email your teacher. Okay.
Well, here we go.
Okay. We got it. We got to take care of technical
Sorry about
difficulties.
that. So Regina, what makes something a vertex figure?
Okay. Can you go ahead and click on that?
Yes.
So basically what it is it's an arrangement of non-overlapping tiles. And then those have to actually add up to 360 degrees. So if those figures do not add up to that, then it cannot be a vertex. And they cannot overlap over each other either.
Okay.
Oh, that was pretty interesting. Great explanation here. I see all your colors. I like this.
Oh yeah.
Yeah, I'm a color person.
It's okay. It makes it very interesting to look at. I love it.
It makes it easy.
Yes, easy to follow along with. You do a great job with that.
Thank you. So Jess, how do we know what to use in place of the n in the formula?
Okay, when we're looking at our formula, it's the interior angle formula. And we are, like you said, looking for that vertex figure. So the n is going to actually be the number of sides each shape has that is making up that vertex figure. So we have a pentagon with 5 sides. We have a hexagon with 6 sides. And then we have our octagon with 8 sides. So when we're looking at is where our formula is, and we see that minus 2 times 180 over n. That n stands for the number of sides. So n, you kind of think of numbers. So if we have a pentagon, it's going to be a 5 since it has 5 sides. So we would put a 5 in right here. And as you can see, that's here on the side. If it's a hexagon, we're actually going to put the 6 in for the 6 sides. Same for the octagon. We would just plug an 8 in, and we would use the same formula for each shape. We just have a different number in place of our n.
Okay.
I understand that a little bit more.
That makes a lot of sense.
Yes, thank you for sharing that.
Write that one down a little bit. Figured it out myself when I did it.
A lot of steps.
It was a lot of steps, but when using that formula, it was pretty easy to follow along with. All right, Danielle, if Mara had used different shapes that added up to less than 360 degrees, would those shapes form a vertex figure?
So, like y'all explained before, these all added up to 363. So it was over, and that didn't make sense. So if you were to go under 360, say you had 353, it's still not going to be a vertex figure. It has to be exactly 360 degrees.
Oh, that's true. I thought of it going over, but with the thought of it being under 360 degrees, I didn't think of that one.
Yeah, I didn't either.
That was a good take on that one, Danielle.
Thank you. Hey, Regina, what is the difference between an SSS property and an SAS property?
So both of those actually have two congruent sides and they both have an angle. But what we know about the SSA property is that we have the two sides and that the angle is not between the two sides. And then when we have the SAS, we have the two sides and the angle is between the two sides. So that's what tells us the difference in those.
I see that. Thank you.
Mm-hmm.
Right.
All right, so Jess, can we use the SSS to prove? And you have your problem written out there?
Yeah. All right. We can actually use the SSS, which is, like you said, side, 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 to prove that triangle QPT is congruent to triangle SPT. So what we can do is look at, and we see that QP, which right here is QP. It's gonna let me write on it right now. So anyways, and we can see over here that SP and QP are equal, and those are congruent. Those are the sides. We can come down here and look at QT and then ST, and those are another sides that are equal or congruent. And then if we're looking at our third side, we see that they actually share a side. So, and that is PT. And of course, PT is going to be equal to PT. So we can use it, the SSS, because all three sides are equal congruent. They all match and they all go together.
Okay.
So
that was a good explanation. Yeah.
Yes, thank you.
All right. Danielle, why is angle SVP a right angle?
Okay. So this angle right here at SVP, how can we determine it is a right angle? So with all these sides being the same, and this right here, these two lines, sorry, that's horrible. But anyways, they're perpendicular lines. And of course, back a couple modules ago, when we have perpendicular lines, all your lines are going to equal 90-degree right angles. So that's why this one right here is a right angle.
That's right. I remember that. Thank you for that refresher.
Me too. My fourth grader is studying perpendicular lines right now, and he is watching Khan Academy videos. That's how he's doing his lesson each day.
That is awesome. I use Khan Academy to figure out what I'm doing.
Yes.
Recommend
I told him. I still use that, so.
Yes, it's great. That's a great thing.
Hey, Regina, how do we make a pentagon with points E, A, P, and T, and equilateral triangle with points Q, R, S?
Okay, if you'll go ahead and click on that, and then it'll start popping up and showing us if we had a pentagon, and then there's our triangle. And basically all we're going to do is we're just going to mark each one of those points and then give them a letter. And I think if you'll click, yeah, there it goes. So each where the two lines meet and actually make a point, that's where we're going to assign a letter for it. And there's 5 for your pentagon, and then there's 3 on the triangle.
Yeah, I love it.
Okay.
I love the colors on your. So easy to read.
Thank you for explaining that.
You're welcome. Okay, so Jess, how did we come up with the 120 and 72 degrees for our angles?
Okay, how we came up with this is we knew that to get our angle NOQ, we had to take angle PON, which was equal to our 72 degrees, and angle POQ, which was equal to 120 degrees. and subtract those to get our angle NOQ. But we got our 120 and our 72 by looking at our shapes, and those shapes have the same number of points and sides, so they're inside a circle. And with those points and sides, we divide how many there are. So for angle PON, we had 5 sides on our pentagon, and we would take 360 and divide that by 5 because of the 5 points and 5 sides. So that gave us our 72 degrees. And then we had our triangle, which has the 3 points or 3 sides, either way you look at it. And that was 360 degrees from our circle divided by the 3 points and sides from our triangle. And that's where we got the 120 degrees and the 72 degrees to subtract and get our angle NOQ, which ended up being 24 degrees.
Okay. Awesome. That's a good way to break that down. Thank you.
Danielle, what kind of angles are POQ and PON?
So our angles POQ and PON, let me go back to the notate, are these right here. Here's PON, and here's POQ. And these are both called central angles. And you'll use those to find your angles in the problem, the rest of the angles.
Okay, do that, the central angles. Okay, thank you.
Oh. Hey, Regina, once we have worked the problem out and found the 330 feet, why are we not finished with the problem?
Okay, if you'll go ahead and click that. So after we go through all the steps of working this problem out, and we find that we have maybe one more time the 330 feet, what we need to know next is that is actually showing a mile away, and she was not a mile away. I believe her name was Jenny. She was actually just a quarter of a mile away. So what we have to do then is we have to take that 330 and we have to divide it by 4, and then that gives us the correct answer of the 82.5 feet.
Great job. I love your little girl on the side over here, Regina.
Thank you.
She looks pretty happy. See,
she is. She's on number 6. She's very happy. Right. So, Jess, after we rewrite our problem, what can we do?
Okay. After we rewrite our problem, we're actually going to convert these measurements. I don't want to work in all these different measurements. So we are going to convert to feet. We are going to leave our height of the cliff because that's what we were looking for. We are going to change, we're going to leave our feet right here. We'll convert it to, sorry. We're leaving our feet, our 2 feet over here, so that's going to stay the same. We are going to convert our 1.5 inches to feet, and that's going to be 0.125 feet. And then our 1/4 a mile, we're going to convert to feet, which would be 1,320 feet. And then you just keep working through the problem until you get your answer, like you said, the 82.5 feet. We just convert it to make it easier to find our solution.
Yeah, it definitely makes it easier by converting those to one measurement.
Yes, definitely.
That's a lot to try to work with. Not doing that.
Yeah, too many different things and too much hassle. Just make it all even, all feet, working with the same. However you want to put it. So much easier.
Yes.
All right. And Danielle, bring us home, girl. How can we find the height of the triangle here?
So say here's Jenny over here, and we have the distance from the eyes of a ruler, the distance from the cliff, and then this here is going to be the height of the cliff. And here's the triangle to show it right here. We've got the 2 feet, and then of course the height of the ruler is 1.5 inches, and then we're trying to find the height over here inside. Took the triangle and put it in right there. So basically, here's the little formula that we would use. But of course, you'll rewrite it like Jessica had, or Jess, sorry.
Same thing. It's okay.
You'll rewrite it to height of the cliff over the 1/4 mile. And then you'll have the 1.5 inches over 2 feet. And you'll finish that out because you're still finding height of the cliff.
Mm.
And we know that a 1/4 mile is 1,320 feet. And when you work that all out, you're going to get 82.5 feet is going to be your height, like Jess showed us.
Yes.
Okay.
I love how you took this triangle and you put it up there actually to show that. Like, that is amazing. I love this slide that you made, Danielle.
Problem looked really confusing until you realize, hey, that's a triangle. We can figure out the side.
Yeah, it's a lot easier to see it that way.
Yes.
To figure out what's going on.
Absolutely.
And I believe that's it.
That's the end of our video. So thank you guys for watching. We hope you are all staying safe during this time. So thank you.
All right. Good night.
Thank you for learning with us.